So let me begin by recalling the notion of leakage-resilient zero-knowledge introduced by Garg, Jain, and Shahai. The setting here is similar to that of the traditional zero-knowledge proof system. There is a prover and a verifier, and the prover wants to convince the verifier that the instance belongs to that language. And to do so, he has a witness corresponding to this instance. However, unlike traditional zero-knowledge proof system, here an adversarial verifier can not only look at the messages he receives from the prover, but he can also get some leakage on the internal state of the honest prover. And in this case, we say that the system is secure if the protocol does not leak anything beyond the validity of the language, as well as whatever you can deduce from the leakage obtained on the internal state of the honest prover. And more formally, you model this as an ideal world, real world paradigm. There is a simulator who has access to a leakage oracle containing a witness. And you say that this system is secure if an adversarial verifier cannot distinguish whether he is talking to an honest prover or the simulator. Okay. So we note that in this case, the leakage of this secret state of the prover is handled only for one single execution. So if the prover has to undergo another execution, then he has to discard the witness and use a new witness. This sort of is unrealistic, because when you implement crypto systems, you implement it to be executed many, many times. And in such scenarios, it is reasonable to assume that the leakage occurs for every execution instead of just one particular execution. And this has been studied under the umbrella of continual leakage setting. And this setting essentially consists of two main phases. In the first phase, you essentially obtain the leakage of the system during all the executions. And in the second phase, you can update this, the secret state of the system is updated in between executions. And there have been many works in this area, and all the well-known primitives such as public key encryption schemes, signature schemes have been constructed in this stronger model of continual leakage setting. But most of these works focus on obtaining non-interactive primitives, barring the last work and the one which you heard in the previous talk. So we want to understand whether we can construct some interactive primitives in the continual leakage setting. And more specifically, we ask whether we can obtain some form of zero knowledge in the continual leakage setting. But before we answer this question, what does zero knowledge even mean in the continual leakage setting? So it turns out that to even define what exactly is leaked from the honest prover is sort of a non-trivial task. In order to explain more about this, I will talk about the challenges we face in order to model this later on. So before that, let me first present the result we have. In this work, we propose a proof system called non-transferable proof system, and we study the security of this in the continual leakage setting. And we show a construction of this non-transferable proof system based on pairing-based assumptions. And more specifically, we base it on external Diffie-Hellman assumption. Okay. We note that our construction is in the CRS model. And even under this relaxation, things don't turn out to be that easy. Okay, so let me first sketch the techniques we use in this work. We use two main building blocks to obtain the construction of non-transferable proof systems. One is the LRZK construction by Garg, Jain, and Shahai. And the other building block is what we call continual leakage resilient encodings, which is the CLR encodings. So combining both of them will give us non-transferable proof systems. So as a result of our techniques and our result, we obtain interesting consequences. The first consequence is we get the first construction of re-randomizable NIZKS for all NP. And the previous works had focused on obtaining re-randomizable NIZKS for some specific NP relations. And the second consequence is that NTP itself implies several primitives such as identification schemes, witness ID schemes, and so on. So we automatically get all these primitives in the stronger notion of continual leakage setting. And surprisingly, the tool we developed to obtain this non-transferable proof system, which is the CLR encodings, itself implies public key encryption schemes, attribute-based encryption schemes, and so on, when combined with witness encryption. We note that several of these primitives are already known are already constructed under well-studied assumptions, but we give a generic technique to achieve all of these applications at once. So let me now sketch what I'm going to do for the rest of the talk. First, I'm going to describe the model of non-transferable proof systems. And then I'm going to give the construction of it using CLR encodings. And then I'm going to give a construction of CLR encodings. And then I'll conclude the talk by giving some open problems. OK, so first, let me focus on the model. So before we see how to model this non-transferable proof systems, let us make some simple observations. The first trivial observation is that a prover cannot store the same witness through all the executions. This is because if a malicious verifier even leaks one bit at a time, then he can get the entire witness after some number of executions. Okay? So this means that it is sort of necessary to refresh the witness in between executions. And we formalize this as an encoding scheme. And more formally, we define an encoding scheme for an NP relation. This consists of three algorithms. One is the encode, verify, and update. Encode algorithm just does some pre-processing on the witness. And the verify algorithm checks whether an instance belongs to that language or not using this encoded witness. And the update algorithm essentially refreshes this encoded witnesses. Okay. So using this encoding scheme, let us now try to define what is a non-transferable proof system. Okay. So now we have a prover and who wants to prove the validity of the instance X. And instead of having a witness, now he has an encoded witness. And now he convinces the verifier that the instance belongs to that language. And after the end of this execution, he will refresh his encoded witness. And now there's a second execution where he convinces again to a different verifier that the instance belongs to that language. And now he uses the new refreshed encoded witness in order to do so. And this can go on. He can convince many verifiers, and in between these executions, he will refresh his encoded witness. OK, so now let us see how to model the security of this proof system. So right now, we have no idea how the security should look like. So let us just shoot in the sky and try to get the best possible security notion. So let us consider a simulator in the plane model. And we say that the system is secure if the verifier cannot tell apart whether he's talking to an honest prover or a simulator. And note that the verifier will get leakage on the state of the prover as well as the simulator. It turns out that this simply does not work. The reason is the verifier can ask some leakage queries that might, in order to answer such leakage queries, you need to know the knowledge of the witness. In the case of the honest prover, he has the witness and he can answer such leakage queries. But in the case of simulator, he has no witness, so he will not be able to answer such queries. So clearly then the verifier can distinguish whether he is talking to an honest prover or a simulator. So this informal argument was given in Garg, Jain, and Shahai, but this sort of presents a significant obstacle in achieving the security notion. So this clearly did not work. So let us go to the second attempt. So let us equip the simulator with more power. The simulator now has access to a leakage oracle containing the encoded witness. So now the attack on the first attempt clearly does not work here, because if a verifier does ask such queries, the simulator can forward such queries to the leakage oracle, and the answers he obtains from the leakage oracle can now be forwarded to the verifier. Okay. So far, there has been no problems. So let us see whether it yields anything meaningful or not. So by the way, note that when I say that he has access to a leakage oracle, to an encoded witness, this witness will be refreshed in between executions. Okay. So in order to see whether this security notion yields anything meaningful or not, let us do a sanity check. No matter what security notion we have, we don't want a malicious verifier to get an entire encoded witness after obtaining many leakages. This is the least we can hope for. Okay? And it turns out that this security notion doesn't even satisfy this basic sanity check. More specifically, it could happen that a malicious verifier can construct an entire encoded witness after obtaining leakages on the encoded witnesses. So from this observation, we can sort of deduce that you need some sort of a basic requirement to be imposed on the encoding scheme. And more specifically, we want the following property, that if you're given leakages on many encodings, you should not be able to obtain an entire encoded witness. And we formalize this using the notion of non-transferability property. Intuitively, this property says the following. Any adversary, after obtaining many proofs from the prover, along with leakages on the internal state of the prover, should not be able to convince another honest verifier about the validity of the instance. And more formally, we will formulate this security notion into two phases. In the first phase, the adversary will interact with the prover over many executions, and in each execution, he can obtain leakage on the internal state of the prover. And in the second phase, once the adversary has obtained all the proofs from the prover, he can now use those things to convince an honest verifier that the instance belongs to that language. And we say that the system is secure if the adversary can convince the honest verifier only with negligible probability. Okay, so one thing I want to mention before going ahead is that we do not tolerate leakage during the update phase. Okay, so let me now give a construction of non-transferable proof systems using CLR encodings. Okay, so for that, first let me explain what are CLR encodings. So CLR encodings, first of all, is just an encoding scheme, and in addition, it needs to satisfy the following property, that if you are given leakages on many encodings, any efficient adversary should not be able to obtain an encoded witness from it. Okay. And we work in the CRS model. In particular, we say that CLR encodings should be secure in the CRS model. Okay, so this is how we are going to construct the NTB proof system. The prover will now receive an encoded witness, which is the output of a CLR encode algorithm applied on a valid witness. And now, the prover will use the LRZK protocol to convince the verifier that the instance belongs to that language. And now, to refresh this encoded witness, he will just use the CLR update algorithm. Yeah, and so on. So the question is, why is this secure? To prove the security, let us revisit the security game. So if you recall, there were two phases, right? In the first phase, the adversary interacts with the honest prover, and in the second phase, the adversary convinces the honest verifier. Right? So now let us consider the case when there exists an adversary who breaks the scheme. In other words, he convinces the honest verifier with non-negligible probability. Now we will arrive at some contradiction. To do so, what we do is that we proceed in steps. In the first step, we replace the honest prover with the LRZK simulator, who now has access to leakage oracle containing the encoded witnesses. Okay. Now, the adversary cannot tell apart whether he is talking to an honest prover or a LRZK simulator from the security of LRZK. In the second step, we are going to replace the honest verifier with the LRZK extractor. And this essentially says that if the adversary was able to convince the honest verifier with non-negligible probability, then the extractor should be able to output the encoded witness with non-negligible probability. Okay. So now let's just focus on the area contained in this green box. This is an algorithm. This is an efficient algorithm that has access to leakage oracles containing the encoded witnesses. And it outputs an encoded witness with non-negligible probability. This clearly contradicts the security of CLR encodings, which says that given leakages on many encodings, we should not be able to output an encoded witness. This proves the security of NTP proof system. So let me now just briefly mention about how to construct the CLR encodings. So a starting point to construct the CLR encodings is to use re-randomizable NIZKS. Re-randomizable NIZKS satisfy all three properties, right? In order to encode, you just compute this re-randomizable NIZK, and the update algorithm is essentially the re-randomization algorithm. And the verify algorithm is very simple, right? Because you just check the validity of the NIZK proof. Now, what about security? So in order to prove the security, we propose a notion called a special re-randomizable NIZK. This essentially has a few more properties other than the re-randomizable NIZK, and I won't go into details because of lack of time. You essentially boost the property of special re-randomizable NIZK to CLR encodings using techniques from Chase et al. And now the question is, how do you construct this special re-randomizable NIZK? To do this, I'll just give a brief high-level idea as to how the NIZK should look like. The NIZK will consist of two components. The first component is essentially a garbled circuit corresponding to the instance of the language. And you also supply the wire keys corresponding to the witness of this instance. And the second component just says that is a proof that validates that the garbled circuit is correctly computed. And to satisfy the special re-randomizable NIZK proof system, we use specific constructions. Namely, we use the Gentry, Halevi, Vaikunthanathan construction from 2010 for constructing the garbled circuit. And we use the Groth-Chahai proofs to validate that the garbled circuit is correctly computed. Okay. So I did not go into details because of lack of time. So let me just give the open problems. The first natural open problem is, can you construct CLR encodings in the plane model? Our CLR encodings was in the CRS model because we were using Groth-Chahai proofs, which is in the CRS model. And the second question is, can you come up with a construction of NTP where you allow leakage during the update phase? And the last is, can you explore more applications of CLR encodings? With that, I conclude my talk.